Hello everyone, today we're going to learn DFS using trees. Well, DFS stands for depth first search and it works almost exactly the same way as a recursive function. So it goes like this. If you follow the red line, this is a depth first search. It goes like this. There we go. And so what I'm trying to say is like this structure basically is a graph, but more specifically, it is a tree. And even more specifically, a binary tree. Because of this kind of structure, there are three possible traversal methods. So in general, we can represent graphs using an adjacent matrix or an adjacent list. However, when the structure is restricted to a binary tree like this, we can also apply binary tree traversal techniques, which is number three, option three. And when it comes to a value, we simply use array or string class if necessary. I mean the value of the nodes over here. But in this example, it is not necessary to use it. So, well, secondly, to describe these relationships, you know, we assigned each node an index number randomly. So when it comes to adjacent matrix or adjacent list, uh, it all starts from zero, always starts from zero. And I just throw in the random numbers, but for the convenience, I'll just write down in order, but you can throw in the numbers whatever you want. And so, and then we use an adjacent matrix or an adjacent list, which is number one and number two. But on top of that, especially with this kind of binary tree, like I said before, we can search the tree using one dimension array. And in a binary tree search perspective, we start by giving the root node the index 1 in this case, which is pretty unusual. And then the left child is assigned by multiplying 2. So 1 multiplied 2 is 2. And the right child over here is assigned by multiplying 2 and plus 1. So it must be 3. And it must be 4 and 5. And since this is the right child, so it must be 7. There we go. So let's jump into the coding part. Well, first things first, I'm going to write down the basic code. So in this example, we're going to use the three different kinds of traversal techniques. But, exceptionally in the binary search method, the root node starts from index 1. So I throw in 1 in this case, exceptionally. There we go. And then for the first adjacent matrix, I'll name it a matrix. Node, the number of the node is 6. And to initialize the adjacent matrix like this, we should put on a 1 wherever there is a connection between two nodes. So node 0, which is root node, is connected with node 1 and 2. It goes like this. There we go. And then node 1 is connected with node 3 and 4. So there we go. And then lastly, node 3 is connected, node 2 is connected with node 5. So we put 1 in the last part, and the rest of the part in this array will be filled with all 0. And we need the vector, which is STL library in Visual Studio, to store the relation using the adjacent list. So in this case, I make it a list, which is our step 2. So I mean option 2. So we need to initialize the A list. Well, node 0 is connected with node 1 and 2, and A list node 1 is connected with node 3 and 4. And lastly, node 2 is connected with node 5. So this is how it works. And especially in the adjacent list, we only store connected nodes. I prefer this approach, this approach, because it is faster and more memory efficient than using an adjacent matrix like this. Just so you know. Well, after that, like I said before, in the binary tree search method, we can search the tree using one-dimension array. So we need the character array and name the binary, and I'll make it bigger. And we don't use the 0 index part. And first index is A, and second index would be B, based on the structure that we went through previously. And index 3 is C, index 4 is D, and index 5 is E, and we don't have the left child, so throw 0, and the index 7 would be F. There we go. And then I'm gonna complete the code over here, the tree1 function, which is related to the A matrix. So we have 6 nodes, as you probably can tell. And well, if A matrix I, now I, has 0, we need to skip it. And to make this code more readable, I'm gonna name I as next. This must be next. So after that, I'm gonna call the tree1. It goes like this. And then I'm gonna print out the value. I'm gonna use casting. There we go. And then I need the space. This. And then with the same method, like it is almost similar, but we're going to use the adjacent list in this case. And so printing the value all are same, will be same. And then we go through the A list now size. And then we have to name the A list now I as a next for the convenience. And we directly call tree2 and throw in next in this case. There we go. Now I'm going to complete the tree3. So tree3 should be now multiply 2. This would be the next value. And then T3 now multiply 2 plus 1. Because all the time in the binary search perspective, they always pick the left child first. Just so you know. And that's why I put now multiply 2 first in this case. So this is for the left child, and this for the right child. There we go. And in this case, in a binary search method, missing nodes must be handled manually. So we need the base case here. So if what was the variable name? The binary, yeah. If binary now is 0, we need to return immediately, and otherwise I'm gonna print out the binary now. So as you probably can tell, you may notice that there is no base case here or here. Why does this work? Because when we reach a leaf node, the for loop simply runs 0 times and the function returns naturally. But on the other hand, as you probably can tell over here, in a binary search method, missing nodes must be handled manually. So that's why I throw in this code. So, well, if I execute this file, well, the result of this kind of using 3 different kinds of techniques is all exactly same. And A, B, D, E, C, F is the order. So it must be like A, B, D, E, C, F. So this is how it works when it comes to DFS. Well, in this example, I'm going to use the adjacent list type, and then I'm going to operate the pass array in this case to see the previous choices that I make. And I'm going to throw in the index number randomly. So for the convenience, I'll throw in the numbers in the order, but you can do whatever you want in this part. Well, first things first, I'm going to write down the basic code. Well, we're going to use the pass, so we need the level parameter in this case. And level. There we go. And then in this example, we have the value, so that's why we need the string class. And we need the vector because we are going to use the adjacent lists. Well, we have 7 nodes, and I'm going to initialize the list first. So the node 0 is connected with node 1, 2, 3. 1, 2, 3. And a list 1 is connected with 4, 5. Node 2 is connected with 6. There we go. And we need the pass array as well to see the previous choices that we make. Well, just so you know, we need to mark the root node first before we get into the DFS related function, because a normal recursive function usually starts from the main function, but DFS always starts from a specific start node, which is T in this case. And so we store that node in the pass first, and then we go deeper. So this is the big difference between a normal recursive function and the DFS function. And when we come back, I'm going to erase it. This is optional. I'm going to show you later. Well, and then we need to spin through a list now size. Then I'm going to name the a list now I as next for the convenience. Now I'm going to record the pass. The reason why I throw in level +1, which is different from a normal recursive function, is because we already mark the root node before we get into this function. So, and then I'm gonna go deeper. So next level +1. And then when we come back, we need to erase the pass. There we go. And then whenever we call the tree function, I'm gonna print out name. So if I execute this file, goes like this: TOHIMNS. So if we take a look at this structure, TOHIMNNS. This is how it works. And so if we take a look at the pass over here, we mark the pass with T, and then TO and H, and then we come back, we erase the H, and then we need to get into TOI, and then when we come back, we erase I and O as well, and then we need to get into TM, which is this part, and then we get into TMN. When we come back, we erase the N, and then erase the M, and then finally we can get S. And when we come back, we erase the S again, and this is all about the three works. And then when we come back, we can erase the root node as well. But the reason why I say this is optional is because that, you know, this is already we're already in the end of the code right now, so this is pretty optional. Well, this kind of pass method can be used not only in the adjacent list, but also the adjacent matrix and even the binary search technique as well in the same way. And so, well, this is all about today's video, and I hope you find it very useful through this video. Well, thanks for watching, and see you on my next video. Bye, guys.